Jai Hind. The topic which we are going to discuss today is Merkle Tree. Before discussing or starting with Merkle Tree, just have a overview of the blockchain, what we have discussed so far. So here, this slide is basically showing the characteristics of blockchain and the different categories of the blockchain. So this we have already discussed, that when we talk about the characteristics of blockchain, we say that it is a digital ledger. Now this digital ledger is being maintained in distributed and decentralized environment. That is, all the in the distributed environment, all the nodes, they are having a copy of this digital ledger, and each and every node is working on its own copy. So it is a decentralized system. There is no central authority or the body which is regulating this distributed network. When we say the digital ledger, then this digital ledger, it is auditable in nature, it is immutable. That is, once you have added the content to this ledger, you cannot update this. This ledger, it provides the trustless environment, it is transparent, and it is maintaining the privacy and the security. It is secure to use as compared to the ordinary databases. And when you are adding something to the blockchain, then we are having the consensus algorithms, that is the algorithms which agreement based algorithms, protocols which are verifying the transactions, and after verifying on some mutual understanding. Here, what is the understanding? It may be a solution to a puzzle or something else, on the basis of which they are making a decision that whether to add the block in the blockchain or not. When we talk about the blockchain, we have already seen what is the meaning of public, private, and the consortium blockchain. Also, we could have another category of the blockchain depending upon the type of the permissions we are providing to the users. One is the permissioned blockchain, and the another one is the permissionless blockchain. That is how to verify the users, how to add the users in the network, how when they are leaving, then what is the effect on the network. That all the things being decided whether the blockchain in the category, that is whether the blockchain is come under the category of the permissioned blockchain or the permissionless blockchain. Now let's start with the Merkle tree. Before Merkle tree, let's discuss the header block. That is, we are aware that blockchain, it consists of different blocks. It is a chain of different blocks. In blocks, what we are having, this is the block header. Here we are having the transactions like this. And how we are forming a chain in a blockchain? This is formed with the help of a hash chain. That is, the hash values of one blockchain, it is referring to the another block in the blockchain. First let us see, that is, what are the contents of the header field here. In the header field, we are having the hash value of previous block. Then we are having a nonce value. We are having a Merkle root. So these are the few fields we are having in the header block. In the hash value of the previous block, that is, this block is containing the hash value of this block. So this is being stored here. Now this is the first block. In this case, the previous hash block value is generally 0. This is how we came to know that whether this block is a first block which is known by the term genesis block or not. Similarly, this may be another block. Again, we are having a block header and a set of the transactions. Now, this block, we compute the hash value of this block, and this hash value is being stored here. This is how the hash chain is formed in a blockchain, and that is how in the blockchain the chains are formed with the help of a hash chain. So here a term comes Merkle root. Now what is a Merkle root? What is a Merkle tree? Why we require to store the Merkle tree over here? All these things we are going to discuss today. So let's start with the Merkle tree. So Merkle tree, when we say it is a tree, so it is a binary tree, and the content of this tree is hash values. So we are saying that this tree is a binary hash tree. It is named after its inventor, Ralph Merkle. So Merkle trees, they are constructed by hashing the paired data, usually transactions at the leaf level, then again hashing the hashed outputs all the way up to the root node called the Merkle root. So here what we are saying? We are saying that this is, suppose this is a tree. It is a binary tree, so only possible childs are 0, 1 or 2. So let's suppose this is my binary hash tree. At the lowest level, we are having the transactions, and we are not storing the transactions on these leaf nodes. What we are storing? We are computing the hash value of these transactions, and we are storing these hash values in the leaf nodes. Clear? So we are having the hash values here, and the hash values in all the leaf nodes. Then we start combining two leaf nodes. So here we are making a pair of the leaf nodes. So this is the first pair, this is the second pair. Now question comes, what if there is only a single leaf node left in the pair? Then what we will do? We will just duplicate that transaction and make a pair. So here in this example, we are having two groups. In each group, we are having the hash values of the transactions. Now we compute the hash of this both leaf nodes. Then we come up and find a hash value. Now this hash value is being stored here. Similarly, we will find the hash value, combine these two hash values and find a hash value for these two nodes and store that hash value at the parent node. Similarly, we will perform this operation iteratively until we reach to the root node, and this root node is known by the name Merkle root, and this is the Merkle root which we store in the blockchain, in the header of the blockchain. That is, instead of storing this Merkle tree, what we are storing in the block header, we are storing the Merkle root in the block header. So this is how the Merkle trees, they are constructed, and they are constructed in the bottom-up approach. It is a Merkle tree is a tamper proof. Why we are saying the tamper proof? Because in this we are storing the hash values of the transactions, and if we make, suppose this is my original transaction, and if there is an attacker who modify this transaction, then automatically this hash value got changed. This impact would be reflected on its parent node. Again, the parent node becomes malicious because it contains a you could say a different hash value other than the original one, and similarly this would impact the root node. So we can easily identify that at which level the things had become corrupted, and that is why we say that this tree is a tamper proof. The hashes in the tree change even if the order of the transaction is changed. As we are aware of the hashing algorithm which we are using over here, the hash property, that if the hash value of these two data items is not equal to the hash value of these two data items. So this is what this implies. That is, if I change the order of the transaction, then automatically the hash value got changed. And this is known as the avalanche effect in the hashing. Merkle is a binary tree. So if the number of transactions in block, so last transaction is duplicated to make it even. Merkle trees, they are used to verify if a specific transactions belong to that particular block or not. So this is the formal definition of a Merkle tree. It is a collision resistant hash function. It is a hash function. So here we are saying that there are no chances of the collision happening over here. We are denoting it with MHT. It takes n inputs. What are these n inputs? These are my transactions. And finally, we are getting a single value which we are saying as the Merkle root hash, which is denoted by H. So what is H? Basically, we are passing some input to MHT and our output is a single hash value, which is my Merkle root. So a verifier who only has the root H can be given an Xi and an associated Merkle proof, which convinces them that Xi was the ith input used to compute the H. That is, if a user is being provided with this H, with this some transaction value Xi and some Merkle proof. We will later see what is the meaning of Merkle proof. If I am provided with these three values, that is, I am having the root hash value, I am having the transaction or the Xi value, that is the one of the leaf node value, and also provided some Merkle proof. Now this per Merkle proof, it convinces that Xi was the ith input which has been used to compute the value hash, root hash H. So in other words, what we are saying, we are convincing them that there exist other xj's such that H is equals to MHT, x1 to xi, then xi plus 1 to xn. This ability to verify that an xi is the element of the ith position against the root hash H without having to store all the inputs is the fundamental power of Merkle tree. If a Merkle proof says that Xi was the ith input which has been used to find out the H, so no attacker can come up with another Merkle proof that says a different Xi dash is not equals to Xi was the ith input. Or we can say an attacker cannot come with a Merkle root H and two values where Xi is not equals to Xi dash with proofs pi I and pi I dash that both verify for the position I with respect to H. What it implies? This says that if I has been provided H, Xi and some Merkle proof, then with all these three things, I can come up with a conclusion that this Xi is the part of my Merkle tree and is at the position, leaf position is the ith position. And also, if someone modify the H and says, okay, this is Xi dash and it is also the part of this Merkle tree, then this again cannot be, then again this kind of attacks can also be easily identified, since at the ith location we are having only Xi which we have already verified and not the Xi dash. With the why? Because here H remains same, this remains same, and if someone wants to modify the Xi with Xi dash, then this is not possible. How the things being done in the Merkle tree? Suppose we are having the transactions, we will in the leaf node, we will store the hash value of that particular transaction. Similarly, we will form a pair of at the leaf node. Then we find the hash value of the parent. Then we find the hash value of AB. Now this contains AB, this contains CD hash value, this contains the hash value corresponding to EF, and this contains the hash value corresponding to GH. At the parent, again we combine these two values and generate the hash value of its parent, and finally we will get the Merkle root. So how the things are being done? Suppose we are having a leaf node, we will find the hash values, we will combine it, and this is how the things are being done. So here, when I got the root value of the tree, it is my Merkle root. So a Merkle proof is a succinct proof of that message is one of the leaves of a Merkle tree. How we will say this thing? Suppose I am saying I have all the data. If I have all the data available with me, then I know what is this? This is my Merkle root. Please give me M2. Now the person who is having the blockchain, he will say, okay, this is the M2. Now the thing comes. The person who is receiving the M2, that person needs to verify, okay, this M2 is the correct one, which I have asked from the blockchain provider. So now what will happen? How I will verify that M2 is genuine? I will provide the M2 value and I will provide some Merkle proof. Now this Merkle proof, for instance, these are the two hash value which I got over here. So this is the Merkle proof. With this Merkle proof, I will try to find out the Merkle root. Now this Merkle root is already being stored in the block, in a block. So this value is also available, but we will use that value to compare the things. Now I'm having the M2. I will compare, I will generate a hash value for this particular message M2. Now here what I will get, this already I have got the hash value. I didn't got the exact data. What I have got? I have got the hash value of that data, and I am aware that in a hashing function it is a one-way function. So I am having these two. Now I will get this value. Let's suppose this is X. I am already, and as a Merkle proof, I have got this from the administrator. Now I have computed this. This I already have. So with the help of these two, I can compute this value. Let's suppose this is Y. Now what will happen? I will compare this Y with this value, because being an user, I am aware of this. Now if these two value matches, so we say, okay, M2 is the original message which I have required and it has not been modified. If the value is different, then something is happened in between the things. Maybe that block has been corrupted, that data message has been corrupted on the way, or it has been corrupted on the chain itself. So this is the things go on, and this is why we say that it is tamper free. So as long as you have the root, no one can deceive you to accept the fake messages. So what is a Merkle root? It is a simple mathematical method for confirming the facts on a Merkle tree. It is basically used in cryptocurrency to ensure that data blocks sent through peer-to-peer network are whole, undamaged and unaltered, that is immutable. They play a very crucial role in computation required to keep the cryptocurrencies like Bitcoin and Ether running. So this is again a kind of a tree. Another example, how to form a tree. Here we are having, suppose now this Merkle root it is not being used in the blockchain itself. It is also used in storing the file information. Let's suppose we are having these 8 files, and for these 8 files, we are forming a Merkle tree with the help of a collision resistant hash function H. So we are having these, then we got this, then we got this, and finally we got this Merkle tree for these 8 files. So every node in the tree stores a hash. The ith leaf of the tree stores the hash hi of the file fi. Each internal node of the tree stores the hash of its 2 children. Hash, the your root node is the Merkle root hash. In this example, we are having H18. You could easily generalize and compute a Merkle tree over any number of files. It is useful to think if computing the Merkle tree as computing a collision resistant hash function, which is denoted by MHT. So we can say that H18, we are passing these 8 inputs to the MHT, and what we are getting the Merkle root. Suppose we have uploaded the files. This is the Dropbox file example. And Merkle tree on dropbox.com, and delete everything from your system except the Merkle root H18. That is how you retrieve the things now. So your goal is to later download any one of your files from the Dropbox and make sure Dropbox did not accidentally corrupt it. That is, you are having these files, suppose, and you have uploaded these files on the Dropbox, and now from your file system you are completely erasing or deleting these files. So later on, when you download something from the Dropbox, how you will identify, how you will verify that these files, they have not been corrupted. So this is a file integrity problem, and how the Merkle trees, they will help to resolve. Again, we have seen what we are having. We are having the root. We are having a file which we want to download. Now Dropbox has sent this file to me, but now I want to identify the integrity of this file. So I will request a Merkle proof. Let's suppose this is the Merkle proof which I have got from the Dropbox. Now what will happen? Since I am having this, I will compute this. Let's suppose this is A. In return, I will pass this thing to the hash function. I will got B, then okay. These 2 information I got, then I compute this, and ultimately I will get the root. So I will verify the things. If this computation which I am getting, it is equal to the real hash H18, then I can say, okay, the file which I have downloaded is the original file, and no replay kind of attack has been occurred in between. So without knowing all the file on my content, I can just verify the integrity of my downloaded file. This is how the things are being done. So, but why does this check suffice as a proof that FI was downloaded correctly? Because Merkle Proof verified this means you were able to recompute the root hash by using FI as the ith input and the Merkle Proof as the remaining inputs. If the proof verification had yielded the same hash but with different file, let's suppose this as the ith input, then this would yield a collision, and we are already using a function H, a function MHT, which is a collision resistant function. So we can use this concept to efficiently prove in a Bitcoin transactions that they were the validated one. So sometimes it is useful for Alice who is running Bitcoin on her mobile phone to verify that she has received a payment which has been done from the Bob. So this is a question whether Bob has paid me, and if he has done the transaction, then my transaction is residing in which block. So if I use the consensus based solution, then this is inefficient, because in this case Alice has to download every newly mined Bitcoin block on her phone and inspect block by block. So it will a time consuming as well as a space consuming, because Alice in this case is relying on the proof of work consensus protocol. If I use the polling based solution, that is voting based solution, then again, if some of the node has become corrupted and says, okay, I am the one and this transaction has been paid by Bob, although Bob hasn't done any kind of transaction, then again it would be a problem. So the best solution is the Merkle based solution in this case. Also, Alice never has to download the full block. She only needs to download a small part of the block, which is called the block header, which contains the Merkle root. So in this case, she will get this Merkle proof, and with the help of this, she will generate the Merkle root, and in one of the blocks, she will match with the header Merkle root, which has been stored in different block headers, and with the help of this verification, she will come to know whether her transaction is residing in that block or not. But the Merkle based solution is still require allies to rely on Bitcoin's proof of work consensus to validate the block headers. Then again, it is a problem. What are the benefits we are getting in a Merkle tree? It provides 4 significant advantages. First, it validates the data integrity. It takes little disk space because instead of downloading the whole block, we are only downloading a block header in this case. Tiny information across the network is being exchanged. So again, the communication overhead is less in this case, and it is also provide a efficient verification method. Why we are saying that the Merkle root or the Merkle tree is essential to blockchain? So if Bitcoin didn't include the Merkle trees, so every node on the network would have to retain a complete copy of all the Bitcoin transactions that have been made, and it is very unmanageable to manage such a vast amount of data on that node. Any authentication request on Bitcoin would require an enormous amount of data which need to be transferred over the network. To confirm that there were no modifications, a computer used for the validation would need a lot of computing power, and that is why for all these problems we are having a Merkle tree. They hash the records in accounting, thereby separating the proof of data from the data itself, thus providing that giving tiny amount of information across the network is sufficient to prove the validity of a transaction. Also, it enabled to demonstrate that both ledger variations are identical in terms of a nominal computer power and network bandwidth. So this is all about the Merkle tree, which we have discussed. How we form a Merkle tree, how we check the integrity of a transaction or a file in a Merkle tree, how we verify that in which block that particular transaction is being residing, whether the Bob has done the transaction or not. So all these things could be answered with the help of just a simple Merkle root, the transaction which we want to find out, and a Merkle proof. These are the references from where I have made these slides. Thank you and Jai Hind.